Hi everyone, in this video we're going to be checking out another machine learning paper which is titled Towards Low-Bit Communication for Tensor Parallel LLM Inference. And speaking of inference, by the way, I will be making a video on VLLM, which is a powerful engine for serving large language models at scale. That might be my next video. So I also want to mention that I'll be starting a new series where we are going to be taking a paper, understand the paper, and then check out the implementation in Jupyter Notebook. Alright, so let's get started. So they are mentioning the fact that tensor parallelism, which is actually important when we have a large language model where we split the computation across multiple GPUs and each GPU performs a computation and then the intermediate results are communicated across multiple GPUs for synchronization. Now here they mention that as LLMs continue to scale in size, that communication becomes a bottleneck. Now they mention that a way to solve that problem is quantization. Now the problem with quantization is that current methods for LLM tend to avoid quantizing the features that tensor parallelism needs. So that communication bottleneck is still there. Now what they propose is for a tensor that has to be sent to another device, why not quantize some part of it to Infer and leave some other parts to BF16 precision. So we are going to be seeing that in detail, and by doing so they mentioned that this method maintains 98% and 99% of Gemma 2 27 billion parameter and also Llama 2 37 billion parameters original performance respectively. Now here's what they propose. They observe that the communicated features across device have a consistent structure. What they mean is they found out that some features actually tend to have higher ranges while others tend to have lower ranges, and for features that have higher ranges, why not leave them in high precision, which is BF16 or FP16, and the ones with lower ranges quantize them to Infer, and they did that without hurting performance. We are going to be seeing that in detail. Okay, so let's go to the second page. Let's look at just what I mentioned. So for example, on the right here, the feed forward block. So we have on the x-axis all the features, so from feature 0 all the way to feature I think 5000. On the y-axis we have the range of each feature. So let's say feature 0, its range is 1, so the features have been scaled. So the maximum tensor, instead of it having maybe 5.0 or maybe 5.6, it has 1. So there's some scaling here, I think, for the sake of showing the diagrams. So what they did is for these features on the left that have very high ranges, they leave them as BF16, and the ones on the right here, these ones, they quantize them to Infer. So this is what they meant by the features have a consistent structure. So this is essentially what they are attempting to exploit. And then after doing that, that tensor could be sent to other devices and that could help improve the communication. Now I'm going to skip this part and go to the core of the algorithm. Here they're essentially defining the tensor parallelism technically. So here they mention wait in attention and feed forward blocks are partitioned across devices in tensor parallelism, what I mentioned, okay, such that each partition can be computed in parallel. Now attention blocks can be split across the head dimension and the feed forward blocks can be split across the intermediate feature dimension. So let's say we have a feature that has 4 columns and we have 2 devices. The first 2 features will be sent to device 1, the second 2 features will be sent to device 2, and similarly the weights will also be distributed in a way that communication becomes parallel and also accurate, so that if you do the same on a single device, you'll end up with the same result. So let's look at how it is when we have a single device. Let's say the input is x, the w is this, we have bias. So the dimension of x is, let's say we have one single data point and input features is d, and the weight is going to be d by e. E is what you select and b is going to be 1 by e. By the way, you can check my first video on how PyTorch selects the dimension of the weight and bias based on the input. So this is how it is on a single device. But when we have multiple devices where the input is split across multiple GPUs and we have just a single data point, the features are distributed across the device. So d, which is the input dimension, will be divided by n. So essentially xi, which is I is the device index. So the input at device I, the dimension becomes 1 by d over n. And similarly for the w at device I, the dimension becomes d over n. And then the output dimension stays the same for n devices. So at each device, the computation really becomes xi times wi. And after each device performs the computation, here what we do is we sum the the partial results plus the bias to end up with a result as if we had one device. Now they mentioned that this operation requires communicating FIXI, which is this, the partial result at device I for each device, which can be expensive for large batch sizes and long sequences. What they did is they define compression and decompression functions CI and DI, so that when we have FIXI, we compress it and then decompress it, we should be able to get the input approximately. So what they did is they chose CI, DI to be quantization and dequantization operations. Now here's the same operation. So let's say we have two devices. Device 1 has this, device 2 has this. So what they did is for all the features across different devices, they get the aggregated quantization range. So here it is across all the features and also across all the devices. So for example, the first feature on device 1 and also device 2, its range is 0.1. For the second feature in device 1 and device 2, the range is 0.5. For the third feature, the range is 4. So they use top K. So let's say K is 2. For example, here they pick the maximum here, 4 and 10. So this one's feature 3 and also feature 5 will be left in brain floating 16 when sent to other devices, and all of the remaining features will be quantized to int4. So here they quantize it, but notice that the third and the fifth features are left in BF16 precision. Similarly here, now communication becomes easier. This device sends this tensor to this device sends this tensor to this. After doing that, that tensor is dequantized, this tensor is also dequantized, and there's this summation. Similar operation is done here, and then they end up with this partial result. Now let's look at the method they use for getting this aggregated quantization ranges. They start with this calibration. Let's say we have n devices and e number of output features. So for each feature at each device, they track the minimum and the maximum value. So the minimum value at device I at feature J is 1 minus gamma times the previous minimum plus gamma times the minimum of the partial computation of X times W. And similarly here, the maximum at device I for feature J is 1 minus gamma times the previous value plus gamma times the maximum of the partial computation for that particular feature, which is essentially X times W of that feature. I hope that is clear. So here they mention for the first sequence, by the way, gamma is constant. For the first sequence, Mij is this. For the maximum, it is this. So using symmetric quantization, also range of feature J on device I is essentially negative of the minimum. The minimum is typically negative, so negative of negative becomes positive. And then they taken in the maximum and then they multiply by 2, I think, to get the full range. Now for the experiment, they use 256 random wiki text for the calibration in order to track the minimum and the maximum. The gamma is 0.01. Now here's how they got the aggregated ranges across all the device. What they do is for a particular feature J, for each device from device I to N, they sum all of the RIG that was computed here. And then as a solution, we select the top K features based on RG to be communicated at higher precision. Let's go to the experiment. So they use actually 4.2 bits per value. I'm not going to go into that, you can read it, but we have seen the core of the paper. Let's look at the result using zero-shot accuracy. So they tried multiple benchmarks and then different methods. So for example, the pure JAMA 2 27 billion parameters across all these benchmarks. They also tried quantizing everything to int4. They also tried int4 plus randomly selecting some features to be in BF16. And then this is their method, which is a combination of int4 and then intelligently selecting some features to be in BF16. These are the best results, which is actually their method. This is for llama and this is for another large language model. This is the result in diagram, and this is more about the result. So this is the conclusion. They mentioned in communication they use all reduce, where a device sums its intermediate result plus the result from other devices. That is what we call all reduce, and there are different ways to implement all reduce, and for their way they use all gather. But another way to do all reduce is ring all reduce. So devices, I think, are arranged as a ring. So a device performs a computation, it shares the immediate result with the next next device, which shares its immediate result with the next device. The communication is like in a form of a cycle. Let's solidify what we understood here in the Jupyter notebook. Let's go to Jupyter. All right, so let's see how it works. I'm going to be using two devices for my example. I'm going to start by importing Torch and also Matplotlib. I'm going to use it for a diagram. Now, these are some utility functions I created just for the sake of printing tensors. So to show you how tensor parallelism works across, let's say, two devices, I created a very simple example. Let's say this is X, this is W. If you have a single device, the result of the multiplication becomes this 26 tied to 1. But if you have two devices, what you can do is give device 1 this part of X, device 2 this part of X, and device 1 this part of W, device 2 this part of W. Device 1 performs the multiplication, device 2 performs the multiplication, and you end up with this for device 1, this for device 2. At the end of the day, all you have to do is sum them, and you end up with the results as if you had one device. Now let's see the core of the algorithm. So I define SDE. S is like the number of tokens that we're going to be using. D is the input features. E is the output features. So I created this split input dimension. So it takes in X, W, and also the number of devices that you have. It splits X and W so that they could be sent to the number of devices for the distributed computation. And there's also this tensor parallel sum forward that we are going to be using for the calibration. So it takes in X and W number of devices. It then utilizes this split input dimension. After doing that, that split input dimension function returns X parts and W parts, which are meant for multiple devices. It performs the intermediate computation as if they are on multiple devices, and performs the summation also. So it returns both the partial computations across the different devices and also the final summation. I created this X demo and W demo just to show you how this works. I'm just going to print it in here. So this is X, this is W. If we have two devices, this is going to be the partial output of device 1, this is going to be partial output of device 2, and then this is the summation. Now let's look at the calibration. I started by creating this utility function which checks in the minimum, maximum, and returns the symmetric range that we saw in the paper. And I also have this function that updates the min max across multiple devices and across multiple features. So I created this calibration batches, two batches. I have this gamma, and initially for tracking the min max will be none. Now I iterate across the calibration batches. So I take the batch index and also the batch itself. So I call this tensor parallel sum forward that we saw before. It returns partial computations. So for the partial computation, now we need to look at for each feature the min and the max. That's what we have here. For each feature, the min is this and the max is this. And then call this update track min max. So it takes in the old min, the old max, and the current min and the current max. Current min and current max are gotten from essentially the partial computation, which is X times W. So for a feature, the current min is going to be the minimum value for X times W, which is this. Don't forget we got it from this partial calibration from tensor parallel sum. It also takes in gamma. When we have the new min max, we take 1 minus gamma times old min plus gamma times the current min. Similarly, new max is 1 minus gamma times old max plus gamma times the current max. So we return the new min max. We track them in this list. So let's print it. All right, so initially min max is none. For batch 1 device 1, we have the current min and also the tracked min max. For batch 1 device 2, we have the tracked min max, which are the latest min max across the features that we have. We do the same for the second batch. At the end of the day, for each device, we look at the range. Let's look at device 2 for example. We just have to look at the tracked min max, which tell us the latest min max across all the features. Using the symmetric range, in here the minimum is -2, the maximum is 1, and remember in the formula for the minimum we take the negative of it, so this -2 becomes 2. Okay, 2 and 1, the maximum is 2. We multiply it by 2 and then we end up with this. So that's what we have for here. After doing that, all of this are result result from multiple devices. Now we need to aggregate the result essentially by summation. So the range of feature 1 is going to be 4 plus 4. Let's print it. Notice that feature 2 has a range of 60, which is really high. So for this feature, it should be left in BF16, while other features can be quantized to Infer before sent to other devices. So I created this two functions for quantization and dequantization. So this is just utility functions for quantization. Looking at the diagram, what we're going to do is device 1 has its tensor, device 2 has its tensor. We're going to apply compression where we, for some features, we quantize them to Infer. Device 2 will do the same. Device 1 is going to send its package to device 2. Device 2 will do the same. Device 1, when it receives its package, it is going to dequantize it. So it is going to take the local summation plus the receive package. So this is essentially a function that takes in the selected features that we are going to live in BF16 and also features that are going to be quantized, and also this is the precision. So it returns high precision part, it returns the Infer part, and also the scaling for dequantization. This is a hybrid decompress function which does the opposite of this. Now what I'm going to do is I'm going to simulate what we have in this diagram. Let's say each device perform its computation. Now there needs to be the communication. So this is the device 1 package, device 2 package, where it uses this hybrid compress. So this is the device 1 package. This is the high precision part shape, which is 4x1. This is the Infer part shape 4x3, and this is the scale shape, device 2 the same. Now simulating the communication, I created this device 1 received package, which is essentially going to be device 1 package, and device 2 received package. So the package that device 2 has received is going to be the device 1 package. I created this device 1 reconstruct device 2. So essentially hybrid decompression. Now this is the decompression part. It takes in the package that it's got from device 2 and decompress it. Device 2 is going to do the same and going to print the tensors in here. Okay, now this is the synchronization step. Device 1 synced output is essentially going to be this device 1 partial computation plus the reconstructed device 2 partial computation. So here it is, device 1 output, device 2 output, which is this formula, and this is the original full precision. So when a quantization is not used. All right, I hope this was very clear. Let me know if you have any suggestion for any paper. My next video will probably be on VLLM. I'm really excited about it. All right, thank you very much. See you in the next video.